Today we're going to take a look at section 2.1. This will be the first in the PowerPoint videos I'm hoping to make. As a quick little mention, these are not meant as a replacement to a full lecture or a reading of the textbook, but merely a quick introduction to some concepts and discussing it, so hopefully the textbook makes more sense. So the section name here is the idea of limits, and is a concept we're going to use very heavily in chapter 3 to develop the idea of what we'll call the derivative. The idea is simple. We have here the graph of the position of a rock at various times. So on the horizontal graph, we have time. On the vertical graph, we have its position or the height above ground. So the dot ordered pair right here says that at 1 second, the rock is 80 feet above the ground. At 2 seconds, the rock is 128 feet above the ground. And at 3 seconds, the rock is 144 feet above the ground. The question we have is, how can we describe or talk about the object or the rock's speed or velocity at the time 1? Well, if we use our basic construct or the distance equations, that distance equals rate times time, we can solve that rate therefore equals distance over time. We'll use that in the following slide to calculate a velocity. So here we use the idea that between the time of the instant at 1 second and the instant at 3 seconds, the distance traveled is this distance here, or the calculation made here of 64 feet, over a time duration here of 2 seconds. So over that time frame, we have an average velocity of 64 feet over 2 seconds, or 32 feet per second. However, it becomes pretty clear that this is not necessarily discussing the rock just at time 1, but it's an average velocity of the rock between times 1 second and 3 seconds. We can get a little bit better by changing the second time point we used. If we instead use the ordered pairs 180 and 128, we can calculate a different average velocity to be 48 feet per second. This line should appear to be slightly different than the line from the previous slide, going back just a second here, where now originally we had this slope here, same thing as the velocity we calculated out, and now we have the slope shown here. But again, this is for an entire 1 second interval of time, so it may not be wholly accurate. The idea we're doing in general is looking at finding average velocities, which we can graphically see now is the slope of the secant line. The equation we had used here, maybe in hiding, this one here, which you can find in the textbook, because the change in position or the distance is given by this, the change in time is given by this. If we were to continue this process using smaller and smaller intervals, the top one here is one they actually showed on a previous slide. The rest of these are calculable via a function which is given, did they give the function? I don't think they did actually. Nope, right there. There was the function. So you can make these calculations. What these here are the calculations made like they calculate 48 feet per second, always fixing 1, but changing the second time. Notice they start at 2, then walk closer and closer to 1. So you see the velocities are seeming to approach something. 48.56, that doesn't look like much. We get to 63.84, 63.984, 63.9984. And we look at this a different way. We look at these now in a picture of the that we always kept the fixed at the 80 feet. Here was the 2 seconds, the 1.5 seconds, the 1.1 seconds. We can only show 3 because they get a little bit clustered down here. We're trying to approach what we're going to call an instantaneous velocity by making the time duration as small as possible. Now, as we discussed yesterday, if we set the t delta t to be 0, and the rate being the change in position over the change in time, this is simply thought of as d, would be 0 distance over 0 time, and it wouldn't make much sense. So we want to now think about this being as some sort of convergence of these lines going closer and closer to something that looks like 0 to 0. We can make sense of what this should actually be. Graphically, rather than doing calculations, this would be in terms of slopes. Here is the slope of the line we had first going through t equals 1 and t equals 2. We then get going through t equals 1 as well as t equals 1.5, and also t equals 1 and t equals 1.1. So all 3 green lines are secant lines, as mentioned here, and have slopes 48, 56, and 62.4. They approach what we can call the tangent line. The tangent line is actually a bit tricky to define, but we can define it to actually be the limit of these secant lines. As I keep this blue point fixed, but draw this blue point closer and closer along the black curve, then these secant lines get closer and closer to the tangent line. Another way of thinking about this is if I were to zoom in on the graph at this ordered pair until the graph looks straight, the line I would see would be the pink line. We'll come back to that in a later chapter. So going through this kind of in a general construct now, we have the idea here that we have a secant line here, given by the equation there. And at this point, we see that the secant line is not really what we would think of as being the tangent line, which look more something along the lines of that. Pardon my bad drawing skills. But as we go to a closer secant line, with the values here getting closer, as the two ordered pairs get closer and closer together, we get something that's closer to that secant line. And when the ordered pairs are very close together, it's almost impossible to distinguish between the secant line and the tangent line. So we have this idea that as the t interval shrinks, the secant line approaches what we would call the tangent line, and the slope of the secant lines therefore approach the slope of the tangent line. And because the secant lines represent average velocities and the tangent line represents instantaneous velocities, we have the idea that the instantaneous velocity can be found through a limiting process, or seeing what a sequence of numbers does as it gets closer and closer. So in this case, our best guess at this point is that the instantaneous velocity of the rock at 1 second is given by 64 feet per second. We will see how to calculate this exactly based on the equation given earlier in a later section.